Okay, so now we are in 7.2. 7.1 was just a breakdown of angles and a lot of terminology and basic concepts surrounding those. But we haven't done any trigonometry yet. Trigonometry involves angles, but in particular, we're talking about these things that we call trigonometric functions. If you remember from algebra, a function is basically a rule that takes an input and assigns an output to it. You've encountered plenty of functions. Usually they come in the form of f of x equals something, some expression involving an x. F of x equals x squared, for example. That's a function. Or f of x equals the natural log of x, things like that. Trigonometric functions are the same idea, but with trigonometric functions, or you're going to hear me call them trig functions most of the time, the inputs are angles and the outputs are real numbers that we think of as ratios. Ratios, remember, are fractions, but oftentimes we don't represent the output of a trig function with a fraction. Sometimes we do, sometimes we represent it with a decimal. It just kind of depends on what we need in that moment. So let's talk about these trig functions in the context of right triangles. And then in the next section, we'll expand this to kind of a broader case of angles. So we're working with a right triangle here. And if you remember, a right triangle is a triangle with a 90-degree angle, or in radians, that would be pi over 2 radians. And the legs of the right triangle are the two sides that join together at that right angle. And then we have the hypotenuse of a right triangle, which is the side that's opposite the 90-degree angle, or the right angle. The hypotenuse is always the largest side in a right triangle. Suppose we single out one of the acute angles in this right triangle. And if this is a 90-degree angle, then both of these angles would be acute. They're less than 90 degrees. I'm going to call that angle T in this example here. Relative to this angle T, we can describe these three sides based on their position. So what I mean by that, the side that's opposite angle T, meaning it's the one side that doesn't touch that angle. Notice the hypotenuse and this side labeled adjacent both touch that angle. The side that's opposite we just call opposite. The leg of the right triangle that touches the angle is called adjacent. That's what it means for it to be adjacent. It's right next to it, or it touches that angle. And then the hypotenuse is still just called a hypotenuse. This angle T, it can be plugged into one of the 6 trigonometric functions that we're going to define, and the output of that trigonometric function can be thought of as ratios, different ratios of these three sides. Now, there are a total of 6 different ratios that we can form from pairs of sides in this right triangle, which is why we have 6 different trigonometric functions. The first 3 are what we call sine, cosine, and tangent. And I realized this part got cut off. It should say sine right here. So this is how we spell sine in just English, but written as a function, we just spell it S-I-N. So sine of t, that's how we read that. Here, t is acting as the input, and sine is the name of the function. So this is similar to if you were to write f of t, except now we're looking at sine of t. We define sine of t to be the length of the opposite side over the length of the hypotenuse. So opposite over hypotenuse. Whatever these numbers happen to be, that ratio is what the sine of this angle is. Cosine is defined to be adjacent over hypotenuse. Tangent is defined to be opposite over adjacent. Okay? There's a really common mnemonic device to help you remember these ratios, because these are things that you want to have memorized. It's SOHCAHTOA. It's a made-up word, SOHCAHTOA, but the way we read this is sine opposite hypotenuse. That's the O and the H are opposite hypotenuse. The capital S is for sine. And you can see where that corresponds to this ratio. Sine is opposite over hypotenuse. CAH, that's cosine, which is adjacent over hypotenuse. Tangent, opposite over adjacent. If that helps you, then I recommend remembering that. I remember first time I learned trigonometry, I really liked this little mnemonic device. Now, the other 3 trigonometric functions are actually just the reciprocals of these 3 here. So, for example, secant is hypotenuse over adjacent. cosecant is hypotenuse over opposite, and cotangent is adjacent over opposite. Now we tend to not try and memorize these ratios as they are. Instead, we rely on what are called reciprocal identities. And I'll talk a little bit about more identities a little bit later, but in this case, each of these three trigonometric functions up here is the reciprocal of one of the trigonometric functions down here, and vice versa. So for example, compare sine of t to cosecant of t. Notice that the ratios are reciprocals of each other, opposite over hypotenuse compared to hypotenuse over opposite. Well, one way to take the reciprocal of a number is to do 1 over that number. So another way of saying that that cosecant of t and sine of t are reciprocals of each other are to say either sine of t equals 1 over cosecant of t, or cosecant of t equals 1 over sine of t. Either of these say that these functions are reciprocals of each other. Notice that cosine and secant are reciprocals, tangent and cotangent are reciprocals. Now there's a little bit of confusion that usually happens with these relationships, because your expectation, whether you're realizing it consciously or not, is you expect functions that have the word co in front of them to go together, and the functions that don't have the word co in front of them to go together. And the opposite is actually what's true here. The reciprocal of sine is not secant, it's cosecant. And the reciprocal of cosine is not cosecant, it's secant. It's sort of the opposite of what you expect it to be. That's just the way that it is. I didn't name these functions. It's just something we have to remember. Okay, let's do some examples here. So far, we haven't done any actual examples. We're just going over some definitions. But in this example, we're given a right triangle, and we're asked to determine the value of all 6 trigonometric functions evaluated at theta. You notice that there's an angle here that's singled out, and we're calling it theta. This right triangle looks like it's flipped on its side because the right angle is showing up all the way up here, and that doesn't matter. What matters is how these 3 sides relate to this angle theta. Now you'll also notice one of the side lengths is missing. I'm given 2 of the sides and I don't have the third. That's not by accident. With right triangles we have the ever useful Pythagorean theorem, which relates the 2 side lengths of the legs of a right triangle to the hypotenuse. You may remember the Pythagorean theorem as a squared plus b squared equals c squared. Okay? Now, in the case of a right triangle, a and b represent the legs of the right triangle. And it never matters which one you call a and which one you call b. But what does matter is that the hypotenuse, which in this case is 9, of this right triangle is c. It needs to be c. Okay? So if I fill in some unknowns here, let's say that 6 is a. I can say that 6 squared plus, if 6 is a, then b would be the unknown side. So I'm just going to call it b squared equals c squared, which is 9 squared. This is something that I want to solve. So this is the same thing as 36 plus b squared equals 81, which takes me to b squared equals, I would subtract 36 from both sides, that's 45. And that tells me that b is the square root of 45. In algebra, we learn how to simplify radicals. This simplifies to 3 root 5. Okay? You should know how to do that from algebra. We're not going to take the time to review that here. That tells me this side length, 3 root 5. Okay? Now that I know all 3 sides of this right triangle, I can go through and find the values of all 6 trigonometric functions at this theta right here. Let's begin with sine of theta. What is sine of theta? Well, thinking of SOHCAHTOA, sine of theta is opposite over hypotenuse. The opposite side is 3 root 5. And you notice I start at the angle and I look to what side is opposite that side by jumping up to the other side of the triangle. That goes over the hypotenuse, which is 9. Okay? This can be simplified. 3 over 9 is 1/3. The root 5 up there turns this into root 5 over 3. Okay, so sine of theta in this example is root 5 over 3. What about cosine of theta? Cosine of theta is adjacent over hypotenuse. 6 over 9, or when simplified, 2/3. What about tangent of theta? We know that tangent of theta should be opposite over adjacent. That's from our definition. So we have 3 root 5 over 6. We need to simplify this as well. The 3 and the 6 do some canceling. I get root 5 over 2 in this case. That's 3 out of 6. We're halfway there. Now we need, go down here for this one, cosecant of theta. I'm going to do that next. Okay? Now, cosecant of theta, I can think of in two different ways. I can think of it as it was defined up here as hypotenuse over opposite, or, and this is the way I prefer to think of it, and this is the way that I guarantee it's going to be better if you remember it this way, cosecant is the reciprocal of sine. So why does that matter? Well, we've already found sine, haven't we? It's root 5 over 3. So the reciprocal would be 3 over root 5. Right? Now, I could, I guess, technically leave it this way, but in algebra, you learn that mathematicians generally don't really like having radicals in the denominator, so we do a process called rationalizing the denominator. Now, a quick comment on that. The truth is, mathematicians actually generally don't care. That was a lie that you were told by your algebra teacher. However, there are reasons in some instances to want to rationalize. Historically, the reason that fractions were rationalized was because of back before we had calculators, if we needed a decimal approximation for this, we were taking an integer and dividing it by an irrational number. If you try doing that with long division, it's actually impossible to do without heavily rounding. However, doing it the other way around, if you divide an irrational number by an integer, that's a little bit more doable with long division. But we have calculators now, and that's not really an issue anymore. However, I am still going to ask you to rationalize, and it's for a different reason. In 7.3, we're going to find the sine, cosine, and tangent of several different angles, and if we rationalize the denominators in our answers, a really useful pattern emerges that helps us memorize the important trig functions, the trig functions evaluated at these important angles. So there's actually some memorization techniques that are useful if we rationalize. So I've blabbed on and on about this enough. Let's go ahead and rationalize this denominator. How do you rationalize the denominator? Well, in this case, if I have a root 5 down here, I would multiply by root 5 over root 5, and the answer becomes 3 root 5 over 5 after simplifying. Okay? Secant of theta, what should that be? Well, that's the reciprocal of cosine. And the reciprocal of cosine, if cosine is 2/3, would be 3/2. Do not write that as 1/2. Leave it as an improper fraction. Mathematicians are far more fond of improper fractions than they are mixed numbers. Leave it that way. Cotangent is the reciprocal of tangent. We found tangent here. Its reciprocal is 2 over root 5. Rationalizing this gives me 2 root 5 over 5. Okay? Quick comment before we move on. We found all of the answers that we were looking for. Here. Now, I went up here and I did the Pythagorean theorem to fill in that missing side. But that's review. The Pythagorean theorem is something that you really need to have on lockdown by the time you're in trigonometry. I went through the steps of writing all this out. In future examples, I'm going to jump straight to this. I'm going to say, oh, this leg is 6, this hypotenuse is 9. By the Pythagorean theorem, this leg would have to be 3 root 5. And I'm not going to take the time to show you all this work. I'm trusting that you can fill in those gaps on your own, okay? And that's something that's going to happen more and more as you progress through math. Once you get into calculus, problems tend to take a lot more time than they do in previous math courses. And your instructor is not going to go through every single little tiny step of those problems. They're going to trust that you know algebra well enough to fill in the blanks. Okay, so that's going to be something that you're going to see here more and more. All right, so now in the previous example, the one we just did, we were given that right triangle, and we were shown the angle theta in the picture of the right triangle, but we weren't told what its measure was. And we were still able to use it to find those trigonometric functions, because the functions are ratios of side lengths. So not knowing the angle theta wasn't important as long as we knew 2 out of the 3 sides of the right triangle. We were able to solve that problem. However, there's often times where we need to take the sine or the cosine or the tangent or any of the trig functions of a specific angle where we're told the measure of that angle. In the vast majority of cases, you need a calculator in order to do that. However, there are a small number of what we call special angles, namely the angles 30 degrees, 45 degrees, and 60 degrees, and there will be more special angles in section 7.3 that we'll get to. But these 3 special angles, we can actually evaluate our trigonometric functions at these guys without the use of a calculator, just by knowing the angles. And the reason for that comes from something that you learn about in geometry called special right triangles. We're not deriving this here. This is a geometry topic, and I'm trusting that you remember this from geometry. And if not, that's okay. You go back and review it. But underlying this principle is the idea that if you have a triangle, or if you have 2 triangles where all 3 of the angles match up, so we call this one a 45, 45, 90 triangle, because those are the angles that appear in this triangle. Any 2 45, 45, 90 triangles, even if one is larger than the other, has a proportional relationship between its sides. And in geometry, you derive this little rule with special right triangles. If one of the legs of your right triangle, your 45, 45, 90 right triangle, is x, then the other leg will be equal to that. It will also be x. The hypotenuse will be x times root 2. Why is that? Again, I'm not doing the derivation here. That should have been covered in geometry. Those of you in my support class, we will probably go through the derivation of these in that class, but not here. The other special right triangle is called a 30, 60, 90 triangle. In geometry, if you learn the relationship between the side lengths here, if the shortest side, the side opposite the 30-degree angle, is x, then the other leg of that right triangle would be x times root 3, and the hypotenuse would be double this side. It would be 2x. Again, go back and review geometry if you don't remember why these relationships are true. But the benefit of these relationships is that it gives us a means of finding the trigonometric functions at the angles 30 degrees, 45 degrees, and 60 degrees. So for example, if I want to find the sine of a 45-degree angle, notice that I don't know any of these side lengths here. However, sine of 45 degrees, if I use this as my 45-degree angle, is opposite over hypotenuse, x over x root 2. Now that x can vary depending on which 45, 45, 90-degree triangle this is, but once we go to our sine function, it turns out that the x doesn't even matter because it cancels out right here. This becomes 1 over root 2, or after rationalizing, root 2 over 2. Okay? Now what's interesting about that is it demonstrates something that's true of your trigonometric functions for any angle. But in this case, we're looking specifically at the 45-degree angle. Suppose x is 1, then I would have 1, 1, root 2. That would be one possibility for a 45, 45, 90 triangle. Now suppose x is 100. Then these side lengths would be 100, 100, and 100 root 2. Those are two very different triangles in terms of their sizes. One is much bigger than the other. But in either case, if I take the sine of its 45-degree angle, the answer comes out the same. And what this shows us is that the trigonometric functions, these ratios, actually don't depend on how big the triangle is, because sine of 45 degrees will always equal root 2 over 2 and never anything else, regardless of which triangle that 45-degree angle came from. Let's do the next one, tangent of 60 degrees. How do we find that? Well, the 60-degree angle shows up in this 30, 60, 90 triangle here. Tangent of 60 degrees is opposite over adjacent. And in this case, that would be x over root 3 over x. Oh, sorry, I said x over root 3. I should have said x root 3 over x. The x's cancel out again, and I get root 3 as my answer. Okay? Straightforward. Next one, notice we're using radian measure instead of degrees. So I'm looking at the cosine of pi over 6. Well, pi over 6 radians is the same thing as 30 degrees. You can check by doing the conversion yourself. So this is like saying cosine of 30 degrees. Here's a 30-degree angle. Cosine is adjacent over hypotenuse. So x over root 3 over, sorry, I keep saying over when I don't mean it, x root 3 over 2x. Canceling the x's out, we get root 3 over 2 for our answer. Okay, finally, cosecant of pi over 3. Well, what is pi over 3? Pi over 3 is the same thing as 60 degrees. Pi over 3 radians, 60 degrees, same angle. So we're looking at the cosecant of this angle. Now remember, the cosecant of an angle is the reciprocal of the sine of that angle. What is the sine of 60 degrees? Opposite over hypotenuse. So the reciprocal of that would be hypotenuse over opposite. In this case, 2x over x root 3. That's equal to 2 over root 3 after you cancel the x's, or after rationalizing, 2 root 3 over 3. Okay? Now this example shows us, if you think about how we walked through it, we actually thought about how to find sine of this angle first, instead of cosecant. We thought of what is the sine, take the reciprocal of that. And for that reason, it really becomes it's most important to know the sine, cosine, and tangent of these special angles, because you can get the other three trig functions just by flipping those answers over, taking reciprocals. Let's look at a table giving us the values of some of these common angles here. So again, these special angles, 30 degrees, 45 degrees, 60 degrees, or in radian measure, pi over 6, pi over 4, pi over 3. We found some of them up here, but if you go through a similar derivation, you would find the values in this table. Sine of 30 degrees is 1/2. Cosine of 30 degrees is root 3 over 2. Tangent of 30 degrees is root 3 over 3, and so on for the rest of this table. Now, you may be noticing some patterns here. For example, if I go down this column for sine, I get 1/2 root 2 over 2, root 3 over 2. Those exact same values show up in the reverse order if I go down this column for cosine. We're not going to explore that pattern quite yet because we can see the bigger picture in 7.3 when we make this table a little bigger. But here is a table of the values that we can use the special right triangles for when looking at sine, cosine, and tangent. Okay, that's going to be it for this first video. We'll move on in the next one.